that you have read. Okay, I can consider the ones here, but for the attendance, I'm going to consider the title. If I read the title of the last book that you have read lately, I will consider that one as your presence for today. Okay. I hope I was clear for everyone. Now let's start with the class. And last time we discussed, we covered numerical integration, and today we'll cover an interesting topic, which follows like this. Let me see where the board is. So we did numerical integration, and we covered the Newton-Cote formulas. And in the Newton-Cote's formulas, we learned what was trapezoidal technique, Simpson's rule, Simpson's 1/3, Simpson's 3/8, and they were good. And all of these techniques, we improved them considerably by using Richardson extrapolation. Okay? Personally, I find this one very amazing technique, Richardson extrapolation. It's not magic. We can derive how Richardson extrapolation can be used to take out the error which is in the OH square and use two calculations to find a new result which has an error of OH4. Because Richardson extrapolation, this deals with if the error it is like OH squared plus OH to the power 4 plus OH to the power 6. It's very useful to have one calculation of the integral where we have AH, which is equal to the specific value. We call this I1 plus the error, which is OH squared, and we can have also OH over 2, which is I2 plus an error of H over 2 squared. So by combining these, we can write this error as a function of these other quantities, which means that we immediately go to the OH4. So that's what we covered last time for numerical integration. And today we are going to talk about the Gauss quadrature. Now, Gauss quadrature, it's also a very beautiful technique. It's a very impressive technique because this can be used, this can be expanded even for functions which have singularities, okay? And Gauss quadrature, the general idea is this. So we know that when we use the trapezoidal technique, we might have a function that goes like this. And we may want to find, let's say, we want to find the integral between this point A and B. And when we find this integral, we can use the trapezoid method, which is we find what is the function at this point. So we get this height. We find what is the function at this point. We have this other height. So we add these together. So we have f of A plus f of B times B minus A times B minus A over 2. So we can write this one. But at the same time, what we can do is that we don't always have to use the endpoints, okay? Even when you look at different functions, the functions might be changing so extremely. So if you remember, last time we solved an example where we found the integral of the function of sine of x. Probably it's best if we offer that example too. So let's assume that we have sine of x. What is the sign when x is equal to 0? It's 0, okay? So sine of x, it's a function that goes like this. So imagine for a moment, we can do the same argument here and here. Imagine for a moment that we want to find the integral here using trapezoidal method, and the endpoints are 0 and pi. And what we get is that we get 0 plus 0 times pi divided by 2. So we get 0. So it could be smarter if we select some points here in between, such that the errors might cancel out. So we could select these 2 points, okay? So let's consider this one x1 and x2 to denote new points. And then the area would be this. We see that we are missing this. Sorry, let me think for a moment. Yes, we can. No, actually, in this case, we cannot construct it very smartly. Probably the smartest point for x2. Okay, this is a good example, because this x2 in this case, it could be if we pick up an x2 here, and this area might be canceling some other area on the. Let me see. I'm trying to find really a good-looking function, and let's see if this makes sense here. Okay. Yeah, I think that this idea is better if I continue it here. So rather than using these points, it would be better if we select this and this. Okay, and we are going to lose. So again, the function was here, and then if we select this point and this point, the area that we lose here, that we are not calculated in now, might cancel out the area that we miss on this other side. Okay, so the general idea is that not to use the endpoints, but we can use some other points x1 and x2 to evaluate the function. Okay, this is the idea, and we can use numerical analysis techniques to figure out what is the new integral. And the integral, we can write this one. So this can be a function f of x dx. Let's say from point A to point B. We can write this down as a summation of from n equal to 1. Let's write this from 1 to m of any polynomial n Okay, so this is what we are trying to do. We have an integral and we want to express it as a summation.
Professor?
Yes.
A1 is the area?
No, the A now they are coefficients. They are coefficients. So the idea that we want to say here, this AI, these are coefficients, and the xi are new values on x-axis. Okay. So this is how we are trying to reformulate the problem. And I can also add here that these integrations, they can be used so in the most general sense, Gauss quadrature can solve these types of integrals, and these integrals, we're going to approximate them like this. And let me get some space here to write something down. So any integral from a to b of any function w of x of any polynomial Pm x dx, we have to approximate this one to a summation which goes from 1 to n of some coefficients ai times a polynomial of mth order. But this polynomial is evaluated at xi. Okay. Now there is also a so this would be the formula that you may have to. So this is the general expression. The Gauss quadrature that we are going to cover today in detail. It will be the special case where this function omega x this is equal to 1. Okay. Now in the general theory of this numerical integration. this w can even be, as I mentioned before a while, this can be a function which has singularities. For example, a special case would be the following. So we may have the integral of 1 minus x squared times any function f of x dx. And this is going from -1 to 1. Imagine for a moment that we want to calculate this integral using numerical techniques. This function w here, this is carrying the singularity because this part is not defined at the endpoints of the integral, right? Because 1 minus 1, it's 0, so we have a singularity because 1 over 0 is not defined. But the Gauss quadrature, using spatial polynomials or spatial function, we can be able to do this. Today, we are going to focus mainly on this, okay? And even from the textbook, follow, I guess all the examples are given for this special case. We come back to this part. In this part, we have also to construct a relationship between this n, which is the order of the polynomial, with n. So this is going to be something smaller or equal than 2n minus 1. Okay, so where m is the order of the polynomial and n is the number of terms. Okay, so what does this mean? This means that if we have, let's say, if n is equal to 2, if n is equal to 2, this means that we can have 2 terms in the summation, okay? Then what can be the polynomial? So if you have 2 terms in the summation, which means that we are going to have 2 coefficients for the a1 and a2, which means that we are going to have also 2 values where we are going to evaluate this function x1 and x2. So if we have just 2 terms, what can be the order of the polynomial for which we can calculate the integral? Okay, let's see for what values this is valid. Let's take this out. So let's see how successful. So if you want to have just, let's say we can have a function which is relatively complex, okay? And with only 2 values, 2x1 and x2, 2 values where we evaluate the function. What is the number of polynomials for which this gives a satisfactory result? Let's see, we said that if we have 2, this means that n is going to be smaller or equal than 2 times 2 minus 1. And this is smaller or equal than 2 times 2, 4 minus 1, 3, which means that this n it can be 0, 1, 2, 3, 0, 1, 2, 3. What can we say now here? We can say that using Gaussian quadrature, if we want to use just two points, we can find the integral of a polynomial of the 0th order. Okay, what is a polynomial of 0th order? The function can be y is equal to 5. This is it. Or we can have a polynomial of the 1st order in x. What is this? This is something which looks like y is equal to mx plus b. Then, if we have this means also p2 in x and p3 in x. So even if we have a polynomial of 3rd order, and the polynomial of 3rd order is a function that looks like this, even at p3, we can find with relatively good, so this is equal to ax cubed plus bx squared and so on, plus a couple more terms. So with 2 points, we can find the integral of functions from the 0th order to the 3rd order. So this is what we have to do. Now, if you are attentive, let me think for a moment. In 2 minutes, I can try to show you everything that we need to do. And then we will try to derive, let me see, sorry. Okay. So all that we are going to cover in the next 15 to 20 minutes will be, I will explain in a short time. So in order to find this numerical integration, we are going to use some orthogonal polynomials. These polynomials, you can check their names, like Legendre polynomial, Chebyshev, Laguerre, Hermite. Don't worry too much about them. They are beautiful polynomials because they are orthogonal and they obey recurrence relationships as they are given here. So in the second column and the third column, you are given the values of the polynomials when they are of the 0th order, 1st order, and then using the recursive relationship, we can build up the next orders. They can be obtained also from these relationships, all of these polynomials. This part, until we do a couple of examples, this might be a little strange. So the integrals that we are going to find, they are defined as integral from a to b of a function w in x, and then some polynomials lx dx. This w, this can carry, this can have singularities. The error, it can be shown here in this graph, but now, as we said, we're going to cover mostly this type of Gauss Legendre quadrature, where the w function is equal to 1. So everything that we need to do is shown here, and now let's see how we are going to read this table. Okay, I'm talking right now about the final result before we even derive it, just to summarize it. Okay, so let's see now here. Let's assume that we want to write down the integral of a function f of psi d psi going from -1 to 1, and we want to express it as a summation using ai, which ai are the coefficients. If you see here on this table, you have the ai on one side, and on the other side we have the values of psi. Now imagine for a moment that we have a polynomial of 3rd order, or let's assume a polynomial of 5th order, p5. So if the order of polynomial, if we have a polynomial of p5 in x, then we look at this expression, which was on the board actually, and we say that this 5, I think right now you can even pin the whiteboard, and you can follow me here. This 5 is smaller or equal than 2n minus 1, okay? And let's figure out what is n. We have this -1 to the other side, so we have 6 is smaller or equal than 2n, which means that we divide by 2 on both sides, so we get here n has to be equal or larger than 3. So what does this mean? This means that if we are integrating a polynomial of the 5th order, p5, we need to use the values for n3. What n3 stands for, we're going to write it like this. So the result of the integral is going to be equal to the summation of a1 function evaluated at x1 plus a2 times the function evaluated at x2 plus a3 the function evaluated at x3. Okay? A polynomial of 5th order, we need only 3 terms. What is a1? Well, first of all, let's see what are the x's. X's, the function of the x, the values of x, they are shown here in this slide. It's minus 0.77. Minus 0.77. Can you see where they are? And a1, it is 0.55. 0.55. Plus the next a is 0.88. 0.88. Don't get 0.88. The function evaluated at what is? Can you find what is the next point to consider? So we get the 0. We get the 0.77 minus 0.77 minus 0.88. 0.774, and we have also plus 0.774. Okay. So I guess if you have a look carefully at this table, this is the values of x are plus minus the values which are shown here. Okay. So we have these are the values. So here we put 0 plus 0.55 times the function evaluated at plus 0.77. Okay. So this would be a case when we need to integrate a polynomial or an expression which has the highest order x5. Is it clear? Can you read these values? Or if we have a polynomial of let's say of P6 in x, but what does a polynomial P6 looks like? It looks like a times x to the power 6 plus b x to the power 5 and so on. So we're going to follow the same expression, which is 6 is smaller or equal than 2n minus 1. Minus 1 goes to the other side, we get 7 divided by 2, it's 3.5. So n is going to be larger or equal than 3.5, which means that n is going to be 4. If n is going to be 4, we need to evaluate this function. It is plus minus 33. So it's plus minus 33. So it's you will get minus 0.33. This is plus 0.33. We have also plus minus 0.86. So we have this graph extends a little more. And here we have another value, which is 0.86. And this is minus 0.86. Is it clear? And so it looks like the function will be evaluated at this x, will be evaluated at this other x, at this value of x, and at this value of x. And all of these values for of the function evaluated at these x's will be multiplied by their respective coefficients, which are shown here, which are 0.65 and 0.347. Okay. So now this was this is the general idea of Gaussian quadrature. Now, this is so I also tried to help you how to read this table. Okay. Now we can go to the derivation of how we find these specific weights. Let me look for a moment. Yes. So, hoping that, so again, since now these are also visible for the recording that you're going to see later, it looks like in the first case where the polynomial P5, n was equal to 3, if n was equal to 3, we have to evaluate the function at these 3 points in black, minus 0.77 plus 0.77 and 0. We evaluate the function in these 3 values. We multiply with the coefficients that we found out this AI, these A's, they belong to the coefficients. And this would be the answer. If the polynomial was in the 6th order, like P6, it looked like we need to pick out 4 values of x. And these values yes.
Bëj pyetje, në rastin ne do bënim provim me këta, domethënë, këto do ishin cheat sheet, kjo tabela?
Po. So if this was in a test, this is something which you can write this in the formula sheet. Yes.
So këto janë predefined apo jo?
Yes, they are pre-calculated. That's true.
Okay.
So in the numerical analysis textbooks or formula sheets, they are there. And it's not only the only type of quadrature that can be calculated. There is a series of these, and for all of these, there is nice tables, which sometimes in the future you might need to find, let's say, strange integrals or integrals that have even singularities. You go and read the tables. Yes.
Gjithashtu për çdo n tek është një 0 ky profesor?
Yes, apparently yes. So when n is odd, the 0 is always there. Then you get the 0 when n is odd, and then you get this symmetric plus minus value in the x-axis. Okay. But what we did right now, it was just the overview, how to read the table, and how the results will end up being. Okay. Now, let's see how. And let me ask also something like this, or maybe let me think for a moment. Let's assume that we have a function which is e to the power minus x, okay? And we want to integrate from a, which is equal to 0, to b, which is equal to infinity. And we want to calculate the integral that involves this extra function, but we want to use only two terms, okay? We want to have n2. Now, if you want to use two terms in the summation, this means that it's a little, so every relationship that we are going to write down, they are strongly related to each other. And my first question to you would be the following. If we are going to use two terms, how many unknowns do we have? Sa pa njohura kemi ne, nëse n-ja është dysh.
Do të thënë sa është m-ja, profesor?
Jo, edhe ajo është pyetje në fakt, edhe ajo është shumë e rëndësishme. Ne akoma nuk kemi.
M-ja është 3.
M-ja është 3, e drejtë, po. M-ja është 3, po është m-ja maksimale 3, mund të jetë 2. Because let's see here, n can be 2. Let's see what we get here. Smaller or equal to n minus 1. But this was 2. 2 times 2, 4 minus 1, 3. 2 is smaller or equal to 3. So m can be, so here, the moment that we see this m equal to 2, m can be even, this can be even 2, 3. These are possible values, okay? Which is good. But now, if I can repeat, this was an important question, okay? So we have two values, but qa polinomi mund përdorim, shumë e drejtë mund të ketë polinomi gradës 2 ose gradës 3, bukur. But now the question is, what is the unknown? When we use the Gaussian quadrature, what do we need to know? We need to know these and these, okay? So the unknowns for us are the a1, a2, x1, and x2. So we need to know the coefficients that will multiply the function at these values of x, okay? So once you are given this integral again, probably this might be the last time I say this one. Anytime we want to integrate over a specific range, all we need to figure out is we need to figure out this value of ai and this value of xi. So in this case, n is 2. How many unknowns do we have here? We have 4 unknowns, okay? Because we need to know the unknowns are a1, a2, okay? And x1, x2. And we know now what they are because we read them from the table. Good. So if we have 4 unknowns, how many equations do we need? If we have 4 unknowns, how many equations do we need?
4 equations.
Exactly. So we have 4 unknowns. So we have to find a way to figure out 4 equations that are linearly independent. And using those, we have to find these expressions, right? So we need 4 equations. If we have 4 equations, then the trick here is that having 4 equations, this can help us to do the following. So we said that if m is equal to 3, if we pick up, or let's do it like this. The logic line can be the following. N is equal to 2, and for sure, m can be equal to 2. Good. But if m is equal to 2, then this means that we can consider a polynomial of 0th order, a polynomial of the 1st order, and a polynomial of 2nd order. Okay? If we combine these polynomials into the equations to find a1, a2, x1, and x2, they are not enough. Okay, we have only 3 polynomials. But if we use the second option, n is still equal to 2, but n can be equal to 3, which is true. This is a maximum value of the highest order of the polynomial. Then, if we can see, if this means that we are including also the highest power, which is p3. But we can have p0, okay, where p1, p2, and p3 of x, which means that we can have a polynomial in the third order and so on. So if we use p0, p1, p2, and p3, we can make up 4 equations for these. Is it clear? So that's why if you want to find these values, and that's what the numerical analysts do to prepare these tables like cheat sheets for all of us or for engineers, that's what they're doing. Okay, so it looks like probably we might go with this one, at least for the moment, to derive these. And there should be not too much question regarding this. So that means that we need, for P0, we get the term 1. For P1, we have this term x. For P2, we have this term x squared. And for P3, sorry, this is x squared and x cubed. So these are the highest order polynomials, and I need to fill this one somewhere here, so m, because I forget this, 2n minus 1. Right, this means that I can erase it from here. And now, what we can, from this expression, this is e to the power minus x. So now, this wx, let me substitute with a new value. So this e to the power minus x times this polynomial is going to be equal to this expression. And then we can follow like the following. We can get the integral from 0 to infinity, because we have defined them here. Okay, the a and b, they can change, they can be different values. But I'm going to make also a comment about the values of a and b, which are the endpoints of the integral. These polynomials that we showed over the slides, like Laguerre polynomial, the Chebyshev polynomial, they correspond to specific choice of the values of the a and b. Okay? So this integral from 0 to infinity of this e to the power minus x times p0. What is p0? A polynomial of 0th order, which means times 1. Okay? dx, this is equal to a1 plus a2. That's one equation. Another equation is the following. We have the same integral of e to the power minus x times p1, which is now times x, times dx. This is equal to, so we are writing this one each time, right? So we are putting here p1. That means that this polynomial is, this is a1 times x to the power 0 plus a2 times x to the x1, x2 to the power 0. We know that any x to the power 0 is 1. So that's why we can leave this as it was, a2. Now we come here and we write the same equation. The polynomial is x. What do we get here? We get a1, okay, times x1 plus a2 times x2. Okay, and similarly, we have again the same integral, e to the power minus x times x squared. Integral is over dx. This is equal to what? This polynomial here is x squared. That means that this is also x squared. So we get the following. We get a1 x1 squared plus a2 x2 squared. So I hope things are becoming a little more trivial. So again, we have the same thing multiplied by the polynomial of the third order dx. This is going to be equal to a1 x1 cubed plus a2 x2 cubed. Now, this procedure that we are doing right now, you're not going to do this one every day, okay? You're not required often calculate the coefficients. But it's good to see how we derive these. So from here, it looks like we have, let me have a look. We have these equations, and we need to find these. Then, what we need to do is the following. What is the integral of e to the power minus x dx? We can calculate the first one, right? So what is e to the power minus x? E to the power minus x, it's an exponential function which intersects the y-axis here at 1, and it comes down like this. And this is convergent function. We know that this will converge. So e to the power minus x dx, we can integrate this e to the power minus x dx. I'm sure that all of us know this pretty well. So this is going to be, we can insert a minus sign here. We get a minus sign also here, so minus x. So this is equal to the e to the power minus x with a minus. Integral this from 0 to infinity. Then this would be equal to, I don't like minuses here a lot because they are very confusing, especially in the exams. I can take out the minus sign, I can change the signs of the integral, and we get e to the power minus x at 0. What is this equal to? It's 1 minus 0, this is equal to 1. Okay. So a1 plus a2, we got one equation. How did we find it? We evaluated this, right? Then this is equal to 1. Then what is this other equation? This is e to the power minus x. X dx, we follow a similar approach. Of course, we will not do all of them, but just for a moment, this is e to the power minus x, x dx. We can use u dv. U can be, in this case, x. dv is equal to e to the power minus x dx, but I guess du will be dx, and v will be the integral of this one, which is going to be minus e to the power minus x. Now, this is the type of integral of u dv is equal to uv minus integral of v du. So, which is easy for almost all of us, for sure. And then here this is going to be uv, it's minus x e to the power minus x minus the integral of v du. V is minus e to the power minus x, du is dx. Good. This integral, we just found it out. We have to apply the limits here and so on. So they're relatively, it looks like it's a simple calculus, first year calculus, okay, to calculate these. So at this stage, at this point, I think we can enter the results. So the first equation is 1. The second equation is also 1, sorry. This is also 1. This will be equal to 2, and this is equal to 6. So here we have 4 equations in 4 unknowns, and we should be able to solve them, okay? And finally, we find out that from these 4 equations, we get that a1 is equal to square root of 2 plus 1 over 2 square root of 2, and a2, this is equal to square root of 2 minus 1 over 2 square root of 2. Then we find that x1 is equal to 2 minus the square root of 2, and x2 is equal to 2 plus square root of 2. Good. Now, we just wrapped up a technique how to calculate the coefficients for the integration of any polynomial times this specific function, and we found the coefficients and the values of x. We were successful to get this, and often you might notice that in that table that we showed a couple of minutes ago, where we had the coefficients and the values of x, I think all of those numbers except the 0, they are irrational numbers. Okay, they are irrational numbers because the square root of 3 or square root of 2 appear everywhere. Okay, so that's why you cannot write them as a ratio of a over b. So I hope this is this was clear. So this is something that we can all do it. And we calculated the case where this W was e to the power minus x. Similarly, you can also calculate when this W is 1, okay? And this is what Gauss Legendre does, or this is what we are going to cover, at least for today. But the more complex situations, they are not difficult at all. You should not be scared of those. We did a relatively difficult case. We could have picked N3 and we get M, a larger value, or N, we could have picked N is equal to 4. But it's not that we are doing here construction work, so we can... yes.
Ai sistemi është I vështirë për tu zgjidhur për çfarë?
Cili sistem?
Ai me 4 variablat.
Me 4 variablat. Well, we can solve it here, but we know how to find the roots of equations. So we can take out, let's say, you can even just by substitution. It is a nonlinear system, that's true. But we have learned how to solve nonlinear equations in this course. It was in your homework, and you did it pretty well. You had nonlinear equations. Here in this course, we have not solved only linear systems, matrices. We even solved several. So we learned here how to use. Let's say we had two or three or more equations which involved functions such as sine x, e to the power x, tangent x, and you did pretty well even in the homework. If you go back to your notes, I think you can do it. Or
na duhet Jacobi matrix me na duhet një Jacobi matrix me 16 variable, më duket.
Not exactly. Nuk I duhet ajo. Shikoni pak shënimet ose shënimet e javës të kaluara, atë që kemi diskutuar në klasë, ose po shikoni detyrën e shtëpisë të dytën, besoj ka qenë detyra e dytë apo e tretë, nuk ka qenë in the second homework, you had an example where the functions were not linear in x. Okay? So I think don't be afraid. It's not that difficult. I mean, even by substituting, so you get a2, you can extract a2 from the first equation. You write it here, a1 minus 1. Then you can extract a1. You can substitute, you write everything as a function of x1 and x2. And it's not, well, for sure, if you sit in 10 minutes, you can solve it or less. So don't worry too much about it. It's not that difficult. This can be a homework for you actually to set up the program to find the roots of 4 nonlinear equations. So far, you had in your homeworks, I think, nonlinear equations up to 3 equations, I guess. It's not a problem for you to have a 4th. And the x squared, sorry, these are very easy because this is x squared, x to the power 3. Polynomials of any power are always simpler than tangent function or sine function or cosine function. Okay, so I think we should not be too much afraid of those. Okay, so this is how these are defined. Now, I guess I can take out some of these arguments here, and I can just go over very fast. So if we have an integral which goes from -1 to 1, here we can use Legendre. If we have an integral from Legendre, but no singularity, let me call it this way. Which means, what does no singularity mean? This means that this W of x, this is a constant value, is equal to 1. Okay? This is what this means. But if we have, this is from -1 to 1, if we have some singularity, then we have to use Chebyshev Polynomials. And in this course, you aren't responsible actually for the last 3 types of integrals, but I'm just writing them so that because we'll go over the slides to give a brief overview. And if we have an integral from 0 to infinity, we can use successfully Laguerre polynomials. Okay? And then, if we have an integral from minus infinity to plus infinity, we can successfully use Hermite polynomials. Okay? Now, one reason that we include them here on the board is that we just want to make clear somehow that different polynomials, they cover for different integrals with different a and b's. Okay? If the limits of the integral are from minus 1 to 1, we use Legendre polynomials or Gauss Legendre, or if we have from minus 1 to 1 but with singularity, we get this. And it is good to go over and let's see how we can read these slides that we have here. And again, if you allow me to repeat this again, for the attendance, you go to the Google Classroom and you write down the last book that you have read, okay? And don't mention the textbooks like school textbooks, but any other book. Okay, so what I wrote on the board, let's see what, let me see it. Okay, the polynomials, they look like this. And polynomials, we should not be afraid because they are x to the power 1, x squared, x cubed. Let's see what we get next. We're getting, so this is Gauss-Legendre quadrature. This is the most used that we mentioned this one. And now here, this is Gauss-Laguerre. And so these coefficients that are shown here on the slide, we follow the path how we can find these right now on the board, okay? So we picked up the case n is equal to 2, and those roots or the solutions of this system, they appear here. Yes, and again, so yes, we have two values of x and two values of a. Okay, so I hope this is clear from here. Then let's continue. This is a different type of integral, but this the function of w of x, or the new function which is added to the f of x, is e to the power x squared. So if you have any integral which involves e to the power minus x squared and is going from minus infinity to plus infinity, you might have a couple of courses where you might need to do this one. You may use this table, okay? Which means that this f of x can be something like f of x can be any function which looks like 1 minus x squared all squared. Okay, so if you have such a function, that means that your this has a polynomial P4. Okay, because the highest power is 4, and then equal to 4, right? You know now n is equal to 4, you can immediately find what should be the n. N can be 2, 3, or whatever, and you come to this table and you read it. This is the Gauss-Chebyshev quadrature. You look at this type of integral. This is defined for any integral which goes from minus 1 to 1. And we have a singularity, as you can see, because at the limits of the integral, this special function, 1 minus x squared to the power minus 1 over 2, this is not defined at the endpoints. But still, we can find the value of the integral. Now, here we have a different type of integral. It goes from 0 to 1. And this can have a different type of singularity because we know that at 0, ln of x is not defined, okay? ln of x, ln of 0 is not defined. It goes to minus infinity, or it increases infinitely. And this is, so these are some types of integrals, but as we said, we're just going to use the Gauss Legendre. Okay. Presenting, stop presenting. Good. Okay, so now let's see what we can cover next regarding this beautiful topic. This is the Gauss quadrature. So we can look at one example. So let's assume we have an integral from -1 to 1 of 1 minus x squared to the power 3 over 2 dx. Okay, so here we have one integral, and then this one we can write this as the integral from -1 to 1 of 1 minus x squared all squared divided by square root of 1 minus x squared dx. Okay. So we can just reformulate this one like this, and from the tables that we just had a look before a while, this was the case which had a specific singularity. We can go back to the slides, and this was something which can be solved with the Chebyshev Quadrature. So again, this can be from -1 to 1, 1 over 1 minus x squared times the one minus x squared squared dx. Now the first term, this is w of x. Okay. The second term, this is f of x, or this is a polynomial in fourth order of x. And this is the integral. Then we look at this polynomial of the fourth order, and the first thing that we have to look for is we go to this expression here. So n4, what is n? We just follow like this. We say 4, this is equal smaller or equal than 2n minus 1. Then this one becomes 5. You can help me here, over 2n divided by 2. This is 2.5 smaller or equal than n, which means that n is equal to 3. Okay? So we have n is equal to 3. We write this aside, and all we need to do at this moment is just, we need to go to the table that carries the Chebyshev, that had the coefficients for the Chebyshev Quadrature, and we have to figure out, we have to find what is A1, A2, A3, and we have to find X1, X2, and X3. Then we have to evaluate this polynomial. Yes.
How did we come to the conclusion that it is a Chebyshev Quadrature?
Well, it was on the slide that we had to look before a while. So let's
because of the square root of 1 minus x squared?
Yes, exactly. Yeah. Let me share just for a second the slides back. Can you see it? Okay. So Chebyshev Quadrature is shown here. Okay. So if the singularity, it looks if this function has this form, and we look at the rest. So this f of x is a polynomial which is 1 minus x squared all to the power of 2, and yeah, this is it. So what does this say? So the weights ai, they are equal to pi over n. So in this case, n is equal to 3, which means that the weights, let me see, this is pi over, the weights are pi over 3. So we can write them, this is function f of x2, function of f of x3. So the weights, you can take note here, the weights are pi over n, and the values of x, they are symmetric about x0, which means that 1 is going to be 0 for sure. And this is the cosine 2i. So xi, this is equal to cosine, let me have a look here, it's 2i minus 1 times pi. 2i minus 1 times pi over 2n. Over 2n. Okay, so these are the values of and here I is equal to 1, 2, 3. Okay, so if we had a look here, then we just need to substitute here. This is when I is 1, this is 2 minus 1, it's 1 pi over 6. Okay, so it looks like the first value, x, is going to be the first value, it's pi over 6, or cosine pi over 6, and we know that this is square root of 3 over 2. When I is 2, we get 2 times 2, 4. 4 minus 1, 3. 3 pi over 6. 3 pi over 6, this is pi over 2. So we get here cosine of pi over 2, so this is x1. x2 is equal to cosine of pi over 2. What is cosine of pi over 2? It's 0. 3, 2 times 3 is 6, minus 1, 5. 5 pi over 6. 5 pi over 6. What is cosine of 5 pi over 6? Let's have a look here. Pi over 6 is like 30 degrees. So we have here 1, 2, 3, 4, 5. So we're looking at the cosine. This is cosine of 5 pi over 6. This is a negative value. So it looks like this is going to be equal to, so let me write it here, cosine 5 pi over 6 is going to be equal to minus cosine of pi over 6. And pi over 6, it was here, so it's going to be x3 is minus cosine pi over 6, so it's going to be minus square root of 3 over 2. Okay? So these are the values of x. Then, what was the value of a? They were all equal to, they were all constant. Okay? The value of a, they were pi over 3, because they were shown pi over n. So we have here A1 is equal to A2 is equal to A3 is equal to pi over n. And n is 3, so it looks like all of these, the values of these functions evaluated here, will be multiplied with pi over 3 over all of them. So this would be the, let's say, the answer. Now, I guess this will be all that I want to talk about the Gauss quadrature. And personally, I find the numerical integration, I find this a very beautiful topic. Even when I was a student, I liked it a lot. And my favorite topics, even when I explain here in the class, is in fact actually the second and the third, because the most beautiful thing I want to, when I explain in this class, is to explain about the Richardson extrapolation in the numerical differentiation. Okay, nothing beats that. But after that, I like a lot the way or the use that the approaches that it uses. The Richardson extrapolation in numerical integration is a very beautiful technique. And then the Gauss quadrature, where for different function that carries different singularities, I also find this one personally very impressive. Now, we can go. Do you have any question? So, if we have no question, we can go to the next topic, which will be numerical differentiation. Now, before I go to the slides, probably I can write a couple of words. Numerical differentiation, all the discussion, it starts from we can build up everything from the Taylor series expansion. In the first week of the courses, we have talked about the Taylor series expansion because it's on the textbook, but also because it's very essential in deriving a lot of different important properties. So we talked about numerical integration. Now we pass to numerical differentiation. Now, numerical differentiation, we're talking about this type of operator, dy over dx. This is equal to or approximately equal to delta y over delta x. Okay? We know this much, and we know that in the limit, that this one, so this is approximately equal to this, but it's equal to when the limit of delta x goes to 0 of delta y over delta x. Okay? So we do remember this much from the first year calculus. Then the next step that we're going to use will be the following. So we know Taylor series expansion, and what Taylor series expansion does, it's I think we do remember this. For any function which which changes, we can find, if this is x, we can find the values of at some further point as a function of. So Taylor series expansion, it derives the value of the function at x plus h will be written as a linear combination that uses f of x, okay, which uses this value. So we use a distance h from this reference point. We want to find this one as a function of what? Of f of x, as a function of the first derivative evaluated at x. And if this is not enough, we have to add also the second derivative of the function evaluated here. Then if this is not enough, so I'm using a comma here, the third derivative, and so on. And the exact expression is written like this. We have to add, this is we sum over from n equal from 0 to infinity of the nth order derivative of x over n factorial x minus, sorry, this is h. Since we know that the distance between these 2 points, traditionally we say x minus x0, but we know x minus x0 is h to the power n. So from this expression, from the Taylor series expansion, we're going to get all the numerical approximations of an exact derivative like this. So now we are going to look at these expressions, and then our task is to intuitively find out how we can write this, the first derivative of f of x. Okay. Then we are going to use some tricks to get from this expansion. Okay. So you look at this expansion, and it looks a good relationship of a lot of terms. But at the same time, we can also write this one like this. What is f of x minus h? Okay, what is f of x minus h? This can be written as the summation from 0 to infinity of the nth derivative of the function evaluated at x over n factorial times minus h to the power n, right? Similarly, actually, I could put a plus sign here, but let's leave it like this. We can also find what is the value of the function of f of x plus 2h, okay, because f of x plus h, we know it, so we go a little further. This is going to be equal to the Taylor series expansion of the derivative of the n derivative of x over n factorial times 2h to the power n, okay? So this is what we can use, and again, all of these have inside this first derivative, second derivative, third derivative. And let me say, what is the purpose of numerical differentiation? The numerical differentiation is this. Given f of x, so given f of x, the question is to find what is the derivative d over dx of f at x0. So this is our objective. So we'll be given a function and we'll say, okay, find the derivative of this function at some value, at some specific value of x. Now, in order to write down all of these expansion, I had the opportunity to put them together in the slides, and probably I'm not going to write them on the board because they are not very tricky. So here we are done with the Chebyshev Quadrature, or the numerical integration overall. So, okay. So again, we start numerical differentiation. The f of x, it can be determined from an algorithm or a set of data xi, yi. And if this is the case, we know that we can do this by doing the interpolation of data points. And the numerical differentiation, or MD, it is related to interpolation because the function, that we can approximate a function locally by using different interpolation techniques. And we build this interpolation on top of this of a discrete set of data xi, yi. We have now numerical differentiation is ND is related to interpolation. The second way, the Taylor series expansion of f of x about the point xk. So this is how we can relate numerical differentiation. Numerical differentiation has a couple of problems. It's not very accurate. Okay, it suffers from the round of errors, and errors. If we use the interpolation of functions to calculate the numerical differentiation, we know that even when we calculate a function using interpolation, the errors, they are already there. Okay? And numerical differentiation, we are going to, we'll try to make it clear at least a couple of times for today why this has errors, or why the errors are very distinct. So when compared to numerical integration, numerical differentiation is more prone to errors. So it's more prone to an increase of the error for few reasons. Now let's have a look. So in these figures, what we are showing is that actually if we decrease the delta x, that means that we are getting closer to the value of reference, which in this slide is denoted as xi. And we know what the derivative looks like, which is written here on the right side of the slide. And then we move to the next part. So what we wrote on the board, we said that we can evaluate the function f of x plus h as a function of, with reference to the values of the function evaluated at x, like this. So f of x plus f prime times h plus f double prime times h squared over 2 plus f third derivative times h cubed, etc. So we can evaluate these equations a, b, c, d. They are the essential functions, but if we add up a and b, what we get is equation E. If we look at equation E, you can see that we have taken away the first derivative, or all the odd derivatives. They don't appear because they do cancel out, okay? Then we can get, if we subtract a from b, the first equation, the first Taylor's expansion, with the second, we find equation f, which is the sixth equation here on the slide, and we notice that all the even derivatives, they are not existent because they are cancelled out. Similarly, we can do the same trick with by combining the f of x plus 2h and f of x minus 2h, and this is what we observe. Now, you can notice carefully, you can have a look carefully, the difference between E and G. So if you see the E and G, you can observe that the E, it uses the value of the function at the f of x, then it uses, let me look a moment. Actually, maybe this will become clear a little later, but this is all the equations that we're going to combine for this course, what we see in this slide. Now, we can define for the derivatives, if you look at equation f, that's the, let's say, standard one, we see that f of x plus h minus f of x minus h, so this difference, if we divide this by h, this is a derivative, okay? So from here, we have f of x, how we can formulate this one, if we look at, what does the slide say? Let's look at equation f, good. At equation f, we have f of x plus h minus f of x minus h, and if we divide this one by h, we find the derivative, and the derivative in this case is going to be equal to, or if we divide this one by 2h actually, because they are far away from each other, 2h. So this is the whole range. If we divide this one by 2h, it's also obvious here, this is going to be equal to the first derivative of f of x plus the first derivative of f of x plus h squared, because this is h cubed over 3 times 1 over 2h, 1 over 2h times the third derivative of the function. So I'm trying to write this on the board. For the moment, the students present in the class, you cannot see the board, but later you won't be able to see this because we are recording the monitor. So what we wrote on the board, that's what we get. So it looks like if we find the first derivative of the function, that's what we get. So we can write this one as f of x plus h minus f of x minus h divided by 2h minus h squared over 6. Now this h squared over 6, we can throw it away, we can truncate it, or we can consider that this is negligible or too small, and then we denote the same first derivative as what is shown on the right side of the slide, where we show that this term that we have taken away, or this term that we have truncated, this is OH squared. So if h is 10 to the power minus 2, that means that the error is 10 to the power minus 4. So anything that we have truncated away, it is 10 to the power minus 4, which is the fourth or fifth decimal or fifth number after the decimal point. Now, similarly, we can also relate f of x plus h with f of x and f of x minus h. We can combine 3 equations, and we get another central difference approximation. Now, we call this central difference approximation because to find the derivative of x, we are using the values of the function before and after f of x. Okay, so this is what we are doing. That's why it's called central difference approximation. And we can follow the same reasoning, and it looks like in all of these, the first, second, third, and fourth derivative, the error is always h squared. And notice the coefficients. Notice the coefficients. So what we care here is that for the first derivative, we have 1 minus 1. For the second derivative, we have 1 minus 2, 1. Third derivative is 1 minus 2, 2 minus 1. Okay? And so in the courses of signal and systems, you might have defined already the kernels, and these kernels, they are small matrices which can be convolved or correlated with a signal. If this small matrix that correlates with the signal, it has coefficients which are written like this, like minus 1, minus 1, 0, 1, 0, 1. These kernels, whenever you see such an operator which is going to be convolved with a function, you can immediately notice that you are taking the derivative of the function. Okay, so probably you have seen this already, or for sure you're going to see it pretty soon. So these types of kernels, that's what they do. Okay, so they take the derivative. Just that this is taking the derivative over this axis for sure. If the signal is higher dimensional, you might take the transpose of this kernel. Now with kernel, we mean a filter or a matrix which has discretely defined numbers. Now let's go in this slide. We just observe what we had in this previous slide, but we have here just the coefficients. Now you see here that if you multiply 2h with the first derivative of f, let's do it here. So you go back, you multiply the 2h with first derivative of f, and we get the coefficients of, so we can read everything of the previous slide in here. One thing that it's worth noticing is can you find what is the sum of all the coefficients for each row? Sa shumë coefficiente për çdo rresht. So let's look at the second row. We have 1 minus 2 plus 1. It's 0. Then we look at the third row. We have 1 minus 1, 2 minus 2, 1. Again, the summation, they add up to 0. You look at the last row. If you sum them over, you have 1 plus 6 plus 1 is 8. Minus 4 is 0 again. So now, what do we observe here? Here, we notice that if we are trying to find the derivative, if the h is very small, imagine for a moment that h is too small, but h is so small that probably the value of the function f of x minus 2h and of f of x plus 2h are close to each other, and but if we use these coefficients, we are going to get a 0. Okay, so that means it will be 0 divided by h to the power 4, and so on. And the derivative, while it is not really 0, it might get very high because the h is too small. Okay, so just have a look at this one, and that's why I said that my favorite part in numerical analysis is when I talk about the errors in the numerical differentiation. Good. This was the central difference approximation. Now, the central difference approximation is not very good because we cannot take the derivative at the end points, okay? Because if you need to find the derivative at the end points of a specific function, we need to know what is the value of the function before that endpoint. Probably we don't have it. For that, we have non-central finite difference approximation. And for this non-central difference approximation, we can use forward FDA and FDA, Food and Drug Administration, or what is it, FDA, backward FDA, and it can be obtained from equations 1 to h, or a minus h. So if you take equation a minus equation h, you can get these expressions that are shown here. So here, the forward FDA, this is shown here like the f prime is equal to fx plus h minus f of x. It's called forward because we are using the current value and something in progression, forward. But the next one, which uses the value of the function and the value before that, we call it backward. And it's also intuitive to read it this way. Now we have here first forward finite difference approximation. Okay. Okay, so this first forward finite difference approximation, the error is OH. If we go back to the slides, the central difference approximation, the central equation, the first ones that we looked at, the error, it was OH squared. This is something that we have to carefully monitor, okay, because we like to have the error as small as possible. We wish it was OH4. But we started this discussion of numerical differentiation by looking at cases where the error is OH squared. Good. Now, for the sake of not being able to take the derivative at the endpoints, we define the forward and backward finite difference approximation. We solve this problem, but the error is very bad because it's OH. So this is the forward finite difference approximation. This is the backward. You can notice the difference. So just that the coefficients are moving to the left side, and we're using up to x minus 4h. Here we are using f of evaluated at x plus 4h. Here it's minus 4h. Now, because the error here is OH, and it's not enough. We can improve this by using second non-central difference approximation. And again, we can always derive all of this expression by using the equation that we wrote, the Taylor series expansions that we wrote in one slide were 4 of them, and after we combine them, it was 8. So if we take the equation C and we subtract 4 times the equation A, we can eliminate the second derivative of f, and if we eliminate it, we figure out that we can find, actually, even if we look at the first 2 equations, let me have a look. So these first 2 equations, they are A and C. So from the second equation of this slide, we subtract 4 times the first equation, we get the third equation in this slide, which is minus 3f of x, minus 2h, first derivative of f, plus some terms, which are in h squared, times the third derivative of f. So it looks like here, in the 4th line of this slide, we can put together all the terms that include f, but not the derivatives. And finally, we figure out that we can calculate the first derivative of f of x, where the error will be the last term, which we will truncate, okay? And it looks like we are throwing, if we throw away the term h squared over 3, which is this term here, if we throw away this term, then that means that our error is OH squared. So we can write this expression down here. And again, the next thing that we have to notice is we look at the coefficients. What are the coefficients? They are minus 1, 4, minus 3. Again, summation is 0. So it looks like always the summation of these terms is always 0. We can see the generalization of the non-central finite difference approximation. So the first derivative, to calculate the first derivative's coefficients would be minus 3, 4, minus 1. It goes on like this. 2 minus 5 for 1. You can pick up any row. You can add up all the coefficients. They will always end up in 0, which runs the risk of the error increasing too much if the h is too small. Okay? And this is the case, which is very obvious, that the precision error, it takes over the truncation error. If h is 0.1, okay, the truncation error is huge, but the precision error is not that large, okay, because again, we are not 0.1, it's just 1/10 of 10 to the power 0. But the precision error, it starts to beat up the truncation error when we have the h something like 10 to the power minus 4, 10 to the power minus 5. And we have to make this clear with examples for sure. So this is the second non-central finite difference approximation. Now, so these are the coefficients, and this is the time to discuss about, well, this is not, this slide, this is just a reminder regarding what is the accuracy and what is the precision. And here, the errors that are generated in numerical differentiation, they stem from truncation error and precision error. And let me think for a moment if I can construct another argument regarding this and a special case of numerical differentiation. Probably it's not the time. Okay. So now we had first non-central approximation. We have also another type which is called the second non-central approximation, which is a little better. Let's see how, because the previous non-central, it had an error of OH. If you go back to the slides, we can notice it. And finally, we come to this slide where we discuss that the errors, they are equal to the numerical error in truncation plus numerical error in the round-off. Now, the numerical truncation, it increases with step size. So if we draw the graph to show this together, so let's assume this is h, okay? And this is the error. Now, so let's see from here. We know that if we make h smaller, the error should decrease, okay? So we should get something like this. But when h this is what truncation does. Truncation, this means that we cut out a part, okay? So you have a mountain, you truncate the top part, so you just change the kurtosis of a Gaussian function, or you take off the top part, we are truncating it. This is truncation error. Now we have another error which proceeds, which goes like this, which is the precision error. And then there is some critical value, we can call this one HC, where this other error proceeds, and the total error, which is shown here in the slide, is going to be a function that looks like this. So if we're going to solve any numerical problem, we have to be careful when we determine the critical or the best value of h. Okay. Now let's see what we have here. I guess we don't have much new information. No. Okay. So we can take the slides away. And meanwhile, let's see what we can. So we talked about just how to take the derivative of a specific function, and everything was good. Okay, so we used. Okay, so we come again to a similar technique that I can show it again. But probably we don't need to show this in detail. In numerical integration, we use Richardson extrapolation. The same thing can be used also here. So we can refine, we can improve the errors or decrease the errors by using here again Richardson extrapolation. Now, what is the Richardson extrapolation? Richardson extrapolation, it involves the improvement of the value that we want to find. So when we did this in numerical integration, what did we have? We had an integral, which we denoted this one I11, if you remember from the when we denoted this like a matrix-like structure. Then we had another integral, which was done. We wrote this one 2-1, where the h was different, and then we combine these two to get another value. Okay? Now, in this case, we are dealing with numerical differentiation. So what we're going to do is that we will have so numerical integration is over. We assume that we have a first derivative of a function which is calculated using a specific value of h. Good. Then we can decrease the h further by a factor of 2, and this means that we can have this. Sorry, this is still the first derivative. Of course, this is going to be a numerical value that we're going to work with. So here we have h over 2. Then we can find another first order derivative of a certain function where h is 2 to the power 2. Okay, so this is how we divide each time. This is 2 to the power 1. And then we can combine these two to find, again, the first derivative, but now this is composed. And this error here, this is OH squared. And this, combining these two, the error here, it will be OH fourth, and so on. So the same approach, or that we used in the numerical integration, it's going to be also in the numerical differentiation. So let's have a look. I guess, let me check the slides. Probably we had something that I wonder if we have an exercise here. No. I thought I had included it in. No. Probably I took it away. Okay. So that is good. Let's see an example. So we are in numerical differentiation, and we want to see what the Richardson extrapolation can help us to do. And it could be good if we're going to solve this problem, and we'll be done for today. So let's see this example where we have some function which at some equally spaced points, which is 0, 0.1, 0.2, 0.3, and 0.4. This function here is equal to 0. This is 0.08, and 0.2 is 0.13. 0.13. This is 0.16. And the next one is 0.18. Okay? So this is, we have a function, and we know the values at some discrete values, but they are equally spaced. This is worth noticing, and which means that immediately you can also say that, okay, if you are given these values, we can find the derivative of this function at any point using the coefficients that we saw on the slides. We are talking about those coefficients that if we add them up together, we get 0, okay? So now let's see, for example, let's find out what is the first derivative of x. So let's find what is the first derivative of x evaluated at x is 0. At x equal to 0. So for this, let's see. We can use, now you have the slides already. So if you have your slides open, you can go to the second forward FDA. So have a look at second forward FDA. You can go on the slides and you can search for the coefficients. Can you tell me the coefficients that you see there? So since we want to determine the derivative at this endpoint, okay, at 0, we have to use the forward technique, okay, forward finite difference approximation, forward FDA, because we don't have the values of the function on this side. So we have to do this minus this divided by 2h, okay, so that's what we need to, or divided by h. So if you go over those coefficients, we have the following. This is going to be equal to minus 3f0 plus 4 times f 0.1 plus this should be minus because these numbers should add up to 0. We know that. So this is going to be minus f evaluated at 0.2 divided by 2h divided by 2 times 0.1. Okay, so what we used here, a coefficient of minus 3, coefficient of 4 here, and a coefficient of minus 1 here. And we have to calculate these values. So we have 2 times 0, so sorry, 3 times 0, 3 times 0 plus 4, sorry, it's a minus, but anyway, plus 4 times 0.08 minus 0.13. So we have to read the values of x divided by 0.2. Now, this first derivative at 0, this is 0.967. 0.967. That's good. We found this. Then let's try to find what is the second derivative at 0. What is the second derivative at 0? Let me write it like this. For the second derivative at 0, we can still go back to the second forward FDA. So for the second order, the top one, it was the first derivative. Now to find the second derivative, which we are looking for here, we need to include coefficients of 2 minus 5, 2 minus 5, 4, minus 1. Okay? So these coefficients, let me use the board like this. The first derivative we use these coefficients, the second derivatives we use these. And okay, so we'll have 2 times 0 minus 5 times 0.8 plus 4 times 0.13 minus 1 times 0.16. Then all of these, we will divide these by h squared. So,
fine. Here, the coefficient Jan predefined, prop?
We can say yes, because we find these, they were shown in the slides. They were predefined because if you remember a few minutes ago when we started numerical differentiation, we started with having the Taylor-Chase expansion, f of x and f of x plus h and f of x plus h. Combining those, we find, so if you have the slides, let me go for a moment. If you have downloaded,
okay,
you're good.
No problem.
But let me have a look. Let me tell you which slide to go. We have second, no. We need second order. Where is this? We need the forward. Forward, no. We have to look at the second forward. Second non-central. So you can check the slide 38. Okay, so if you have a look at slide 38, I guess you can find these coefficients. Okay, and all of these we derived them. It was a good question. Thanks for asking. But then it looks like probably I don't need to write all the numbers here, but we do 2 times 0 minus 5 times this plus 5. So all we care is that we care about this vector of coefficients which will be multiplied here. So here I'm going to write this one, the summation of all the terms, Ci, Fi, divided by h squared, which is 0.1 squared. And the second derivative here is minus 3.77. Okay, that's the second derivative. Similarly, we can find using if you want to find the derivative at some other point, let's say, if you want to find the derivative at, say, x 0.2, what is the first derivative at x 0.2? What can we use here? We know that using the central difference approximation, we can get an error of OH squared. It is easy. It was very easy. Which means that in the first slide, where we provide the differences for these, we can say that we can use the function of 0.3 and 0.1. So we can say here f of 0.3 minus f of 0.1, sorry, 0.1, divided by 2h, 2 times 0.1. We should be good, because this one should have an error of OH squared, and we get 0.4 here. Okay? But we were forced to use here forward differences because we were asking for the slope of the function right at that edge. Now, this is, let's have a look for a moment. So, what if you want to try, let's use the Richardson extrapolation to calculate the first derivative of the function at 0. Okay, so our next question is to use, okay, we said Richardson extrapolation. I think, sorry, I erased this a little faster than I should have. So the first derivative it was 0.967, 0.967. And the first derivative, it used these coefficients. Okay, let me have a look. It was, and let's also remember the following. So to use Richardson extrapolation, we need to use to find the derivative using h 0.1. And we can do this, and we can also use the h 0.2, because for a couple of reasons, we like to have the h divided by 2 each time, because we'll be lucky to use coefficients. If you remember the coefficients of the Richardson extrapolation, they look like 4/3 minus 1/3, 16 over 15 minus 1 over 15, right? So they were good looking, so it's really good to work with those. So now let's try to identify, but now I think we have to find this first and this second, because we assume that we improve the calculation as we move down the matrix where we write down all the values. So let's find first what is the derivative at 0. Sorry, this is derivative at 0 when x is equal to 0, but having h is equal to 0.2. Okay? That's what we're trying to say here. So then, what do we need to do for that? Allow me to use this part of the board for. So to use 0.2, we're going to have these coefficients minus 3 here. Okay, we jump 0.2, we apply 4 because we're going to use these coefficients, right? They were really good. So we do minus 3, we use the 4 here, we jump another 0.2, we use minus 1 here. Okay? And then we do minus 3 times this value of the function, plus 4 times this value of the function, this is f of x, minus 1 times 0.18. Okay? So if we use this, the answer is going to be 0.89. 0.89. Okay? Now, this is not the best result because we can make the h smaller, and we have these values. So this corresponds to h equal to 0.2. We get this. Now, let's find when h is 0.1, which means that the coefficients that we can use will be the same, but let's have minus 3 here. Let's jump 0.1. We get 4 here. Let's jump another 0.1. We get minus 1 here. So they are the same, but we should use, here we have nothing. So then we continue. 3 times this value plus 4 times this. Actually, this calculation, we did it here in the previous example. And now the result is equal to what we had written before, 0.967. Good. So these are both, let's not forget, these are first order derivatives. Then we know that when you make the h smaller, the result is finer. So this is a better result. That's why this will be multiplied with the coefficients of 4/3, and this value will be multiplied with the coefficient of -1/3. Okay, and the result will be 4/3 times this minus 1/3 times this, and the answer is going to be 0. So in this table, we'll get 0.9927. Now this is the value of the derivative, and this has an error of the order of OH4. And the error in these two values, it is OH squared. Okay, so this is all I want to cover for today, or at least to give a break. Do you have any question? If you have no question, I think we can stop this session and see you in the next session.